The next item that I want us to discuss is the section 2.5 that is described by that says the systems described by differential equations. A linear, we are saying that we are going to start with a linear constant coefficient differential equation. So we are saying that a general order or general end order linear constant. So there are a number of terms here. The order is n, which is described by this n. Then it is a constant coefficient that is described by ak, that can also be described by bk. Differential equation. Then, of course, differential equation is the one that is described as this, and as by the differential equation ddk. Y of t, y is the output, y, and then with respect to time, with the number of the differential operators, dt power k, and so this is the term that describes the differential equation. We are saying that the ak and bk are the real constants, and n is refers the highest derivative of y of t. Such differential equations play a central role in describing the input-output relationships of a wide variety of electrical, mechanical, and chemical, and even biological systems. So for us, we're going to be dealing with the electrical systems, and we are going to have an example of an RC circuit, which is considered in the problem 132 that is going to be found later. And we are saying that in that system, the input x of t is defined as v of s, which is a voltage source that is varying with time, and the output is described as y of t, which is v out, which is at the output. And therefore, in that kind of a system, it might be described by a first order constant coefficient differential equation that is seen at this point, which we are saying that dy of t dt plus 1 over rc y of t is equals to 1 over rc x of t. So this is a general first order constant coefficient. Well, the coefficient is this one, a constant coefficient differential equation. They're saying there is a number of ways we use to find the solution to this differential equation, and the solution can be obtained as y of t equals to y of p, which is the particular solution, plus y of h, yh of t, which is the homogeneous solution. We are saying that yp of t, the particular solution, so that satisfies equation 225, whereas the harmonious solution yh of t, or which is also referred to as the complementary solution, satisfies the homogeneous differential equation that when you set the right hand side to 0. So the exact form of yh of t is determined by some n auxiliary conditions, and we note that the equation 225 does not completely specify the output y of t in terms of input x of t unless the auxiliary conditions are specified. So always what we know about the differential equations, that the homogeneous equation or the differential equation does not always specify the output y of t or the solution y of t in terms of x of t unless we have the auxiliary conditions that they are specified, and that is when we are able to generate y of t in full. So having said that, then we can say that the auxiliary condition can be expressed as described right there, and these are referred to as the auxiliary conditions are defined at some point. So that serves as an introduction to the differential equations that we can use in describing systems. So we will see the actual value of those differential equations when we go to deal with the real systems. But before we do that, before we go further, we are going to start to discuss some concepts of linearity, which we describe as follows. The system specified by equation 2 to 5 will be linear if and only if all the auxiliary conditions are zero. So we are saying that the conditions that we are describing by these auxiliary conditions, if all of them have zero value, then the system is said to be linear. If the auxiliary conditions are not zero, then the response y of t can be expressed as equation 2 to 8, and we are saying that it is not linear, where yz of I of t or yzit is called the zero input response. This is called the zero input response and is the response to the auxiliary conditions. And yzs of t is called the zero state response. It is the response of the linear system with zero auxiliary conditions. So the first one is when the auxiliary conditions are not zero. They give you zero input response, which is defined by y zi of t, whereas the y zs of t is called the zero state response and describes the linear system with zero auxiliary conditions. Now, this can be illustrated in figure 2.2, and figure 2.2 is right here. And it says that if you have input x of t that is going through a linear system, then the output can be described by, I think this is not very clear. The input can be described by zero state output that we have just said here, zero state response that can be complemented by a non-zero state input responses described by zi y zi of t to give you the y of t as a result. So what are we saying here? You're saying that y z I of t and yh of t are not equal. So we cannot say that this is the homogeneous solution to your to your differential equation, because yz of I, that is zero input response, can never be equal to the homogeneous equation. The other thing that you also observe is that the zero state response of your system is not also equal to the particular solution that we use to describe our differential equation, and that in general yzi of t, that is zero input response, contains the homogeneous response, and zero state response contains both. And this can be seen much more clearly in problem 220, which we are going to be focusing on in our later sections. So for now, I think I will leave it at that point, but we will come to discuss it in details when we are doing the problems as mentioned in those texts. So for now, we jump to another concept that is called causality, that we use to describe systems. That they are saying that if in order for a linear system described equation 225, which is our differential equation, or end order differential equation, for that system to be causal, we must assume the condition of initial rest, which is also called initially relaxed condition, that is x of t is equals to 0 for time is less than t naught. That is the one that we call the initial relaxed condition. And that time y of t will still be 0 for time is less than our point where we start observing our system, which is at t naught. And we are going to see that again in problem 143. Thus, the response y of t bigger than t naught can be calculated from question 225 with the initial conditions that we are setting here. We are saying that the initial condition is obtained at t naught. So y t naught is equals to the differential equation that starts with the dy dt all the way up to when it goes to this. I will state the condition of causality, where we are saying now that in order for a linear system described by equation 225, which is area, to be causal, we must assume that the condition of initial rest or initial relaxed condition, of course, we must assume the condition of initial rest. Now, that is if x of t is 0 for time t less than t naught, then y of t will be equal to 0 for t is less than t naught. This is described in problem 143. And therefore, the response for t is bigger than t naught can be calculated from that equation with the initial conditions, whereby we set that y of t will be equal to this derivative, which is set to be equals to 0. And we are saying that this is equals to the derivative by setting y or the time at t is equals to t naught. That will give you the initial rest or the initial condition, and therefore we are able to find the initial conditions that are necessary to evaluate y of t. And we are saying clearly initial rest y0 0 input of t is the one that we are setting to be equals to 0. The next subtopic that we shall discuss is the response of a discrete time LTI system and the convolution sum. And we are going to say, we're going to speak or initially start with the impulse response. And the impulse response, or the difference between what we are discussing now and what we have discussed earlier, is simply that we were previously discussing non-discrete time, which we were calling continuous time LTI system. So now that we are discussing the discrete time, we still go through the same ideas that we discussed about. And the first idea is that of the impulse response. And we say that the impulse response, which is also called the unit sample response, symbolized by h of n, of a discrete time LTI system that is denoted by t, is defined by the response of the system when the input is delta n, or the unit impulse signal. That is, h of n is equals to the system acting on this unit impulse input. Similar to what we did with the continuous time LTI system, we are going to consider the response of a system in respect or in response to an arbitrary input. And if you remember what we said, that we can represent an arbitrary input x of n as an integral of, remember what we said, that x of t in continuous time was expressed as minus infinity to infinity of x of tau d or delta of t minus tau d tau. So this is the representation of the convolution integral in the continuous time. So if you are now to represent it in the discrete time, you just change this to be the sum. It becomes the continuous as tau varies from minus infinity to infinity, and therefore the k becomes the variable that is varying. Of course, it is now discrete time, and then a constant time where we are observing our variable input x is the one that is considered. And if you remember what we said, that when this term inside this bracket is equals to 0, that is when the term of x of k can be obtained, because this term gives us a 1 when the term inside the bracket is equals to 0. Therefore, that is when you're going to have the term inside of x of k. So since the system is linear, the response of the system to an arbitrary input can therefore be expressed. So what we have done here is just to express the arbitrary input x of n as a convolution sum. So this is what we refer to as the convolution sum. And what we have found earlier there is what we refer to as the convolution integral. So we want to express our system in terms of the convolution sum. And we are saying that now, if this is my arbitrary input, it is being acted upon by the operator t, that is the one that we are using to describe our LTI system. We are describing it as a function of t, which we refer to its the input to the response to delta n to be equals to h of n. We are referring, so this is our impulse response, and it can just be described as such. And therefore, what we have simply done is that we are saying that the response of a system y of n to an arbitrary input of x of n can be expressed as a convolution sum. So there's a very important statement that we make here. We observe that we are dealing with an LTI, and LTI means that it is time invariant. And since it is time invariant, we can express the impulse response as the response of the system due to the unit impulse signal. And since this is a part of this equation, we can then replace, you can then put your t here, and what you will end up with is that y of n becomes a convolution of the impulse response h of n and the arbitrary input x of k. And you see that equation 234 indicates that a discrete time LTI system is completely characterized by its impulse response h of n. So how we have defined the convolution sum is summarized in this section, where we are saying now that section 234 defines convolution of two sequences x of n and h of n, denoted by x of n convolved with h of n, giving you y of n. And this is expressed as equation 235. And as I have mentioned earlier, that this is defined as a convolution sum, and it gives us a very significant result. That we are saying that we have a fundamental result that the output of any discrete time LTI system is a convolution of the input signal x of n with the impulse response h of n of the system, which can be expressed as in figure 2.3, that illustrates the definition of the impulse response. So if you have your unit impulse signal delta of n going through the LTI system, the output will be the impulse response described by h of n. But if you have an arbitrary signal x of n going through the same LTI system, the output will be the convolution sum, which is the the arbitrary input x of n convolved with h of n as the impulse response of the system. And that marks the end of lecture 4. So the remaining section, we are going to cover it from lecture 5.